the groundwork for being able to talk meaningfully about probability models. And overall, we want to split the types of quantities that we're studying into two broad groups, basically a discrete quantity and a continuous quantity. And this unit is all about coming up with probability models for discrete quantities. So what are they? Well, in a business analytics context, mostly they're counts. We're counting up the number of items that someone has in a cart, the number of days we have to wait for our shipment to arrive, the number of overdue library books someone might have. So our possible values would be 0, 1, 2, 3, 4, etc. But more in general, a discrete quantity is any sort of quantity that has a finite minimum spacing between any two values. So technically, if we were to go and look at the amount of money that people had in their checking account, that's a discrete quantity because the possible values go in jumps of 0.01, 1 cent. And if wherever we're looking at some sort of random quantity that obtains just, like a color or a state, some short text description, that's a discrete quantity as well. Now, contrast that with a continuous quantity. We'll talk about that at a later time. A continuous quantity has possible values that essentially form a near continuum of numbers. If we had an accurate enough measuring device, well, any possible number inside of a range could potentially be measured. So if we're talking about the amount of time it takes us to go to work, if we're going to talk about the amount of yield of a particular product, say in grams, if we're talking about the length between two sequential cracks on the highway, if we had a really accurate measuring device, there's really no limit to the number of decimal places we could get that number to. So for all intents and purposes, it's like the possible values are a near continuum. There's no finite minimum spacing between values. So, of course, in business analytics, we're going to blur the line between these two quantities a bit because very often we can justifiably go from one world to the other. So, for example, we might have an inherently continuous quantity like length or time that we can just create a discrete variable out of by coming up with categories. So time might be measured in terms of 3 categories like short, between 0 and 10, medium, between 10 and 30, and long, 30 plus. Likewise, if we're going to be studying temperatures and the distribution of temperatures, say over the course of the year, we might just round temperatures to the nearest integer, in which case there is a finite minimum spacing between possible values, 1 degree here. So depending on how we actually treat the numbers, we might be able to treat a continuous quantity as a discrete quantity, and actually vice versa as well. If we're going to study something like the population of cities, technically that would go from maybe 1, 2, 3, up into the millions, tens of millions even. For all intensive purposes, there's so many possible values, and the minimum spacing between possible values is so tiny compared to the range of values we might see, that it's like we have a near continuum of values. And it might be a little bit easier to actually model them as a continuous quantity instead of coming up with a count model for them, a discrete model. So we'll kind of blur the lines between discrete and continuous, but overall this unit's going to focus on discrete quantities, mostly counts in business analytics, and what probability models are applicable to them. So we can't really have a discussion of a probability model without introducing some of the formalism that's been laid down over the years. If you open up any sort of probability textbook, if you go to Wikipedia and start looking at probability distributions, you're going to see this word, and I want to make sure you're familiar with what this word means. And the word is random variables. I guess it's more of a phrase. So a random variable in business analytics for our intents and purposes is just some quantity whose value might vary from individual to individual. And so we just want to be familiar with the terminology and the notation for how we refer to a random variable and how we refer to the possible values that it might take. So one thing we might study is the number of items that someone has in a cart at checkout. So the name of our random variable we're going to denote with a capital X, and that's going to represent this random quantity, the number of items someone's going to have in their cart at checkout. Now, what we're going to do is represent the possible values that that random variable might take with a lowercase x. So 1, 2, 3, 4, however many items that person might have in a cart. Capital X is going to be the name of the random variable. Lowercase x is going to be the list of possible values it might attain. And you can imagine back in the day when stuff was being taught just on chalkboards or overhead projectors, that this caused a lot of confusion. There's not much of a difference between an uppercase X and a lowercase x when people are handwriting it. So it's nice that we have PowerPoints and PDFs to make this distinction a little bit clearer. So just remember, capital X, that's the name of our random quantity. Little x, that's going to be a possible value that random quantity might obtain. So when we talk about a probability model, we're going to talk about the probability model for a random variable, some random quantity whose possible values might vary from one person to another. And we're going to describe a probability model for a discrete quantity, like a count, via its probability mass function, or PMF for abbreviation. So what is this PMF? What does this probability model consist of? Well, it simply consists of the list of possible values, our little x's, that we might observe, and the corresponding probabilities for each of those outcomes. And we might represent this in a table form. We might have one column that gives us all possible values that might be observed, like green, red, yellow, if we're studying the outcome of a stoplight, and then a second column that gives the probabilities of each. Or we might have an equation where we can just throw in a value of little x, a value we might observe, into the equation to get its probability. So we might model the number out of 4 promotions that someone actually uses when they get emailed a booklet by the equation 0.34 times 0.75 raised to the x. If the possible values we might observe are 0, 1, 2, 3, 4, we could just get the probabilities of each of those by throwing that number into the equation. So a very nice compact way of representing the possible values and their respective probabilities. So can we have just any list of numbers represent the probabilities of the outcomes? Well, no, there are some requirements on what is a valid PMF. So number one, obviously probabilities in a PMF have to be between 0 and 1 because all probabilities are between 0 and 1. Also, because we're going through the list of all possible outcomes, the sum of those probabilities has to equal 1. If it didn't equal to 1, there must be some value that's possible that's been left out, and by definition, the PMF needs to list all the possible values. So the sum of all those probabilities has to be 100%. And likewise, when we go and specify, well, what are the possible values of little x, those values need to be mutually exclusive. And so the nice thing is that when we use a probability model to figure out the probability of some combination of outcomes, like what's the probability of x1 or x2, we just get to straight up add the component probabilities. All right, so with that in mind, we're actually ready to start designing our own PMFs to model the inherent variability in processes that are interesting to us. So one thing we might be interested in studying is the number of customer service calls that someone makes, say to AT&T, per month. So if I gave you a table to represent the PMF with possible values 0, 1, 2, and 3, you'd be able to fill in that table with a valid set of probabilities. We know that the sum over all those probabilities have to equal to 1. So if I gave you 3 of those 4, you'd be able to immediately tell me what the missing one was, because that missing one has to be the value that makes the total sum of them add up to 1. In this case, 0.92 plus 0.03 plus 0.02 here adds up to 0.97, so that missing probability of someone making 3 calls to customer service must be 3% in order to make the sum of those equal to 1. More common of a task, really, isn't filling in, one missing probability, but it's converting, say, a shape that describes the frequency distribution of the different possible values into a bona fide probability model. So we might have a shape that we really like that describes what values are more likely, what values are less likely, but we want to convert that into a genuine probability model. So, for example, let's imagine that we wanted to come up with a probability distribution that had the following properties. So any value between 1 and 100 is possible, but larger values are progressively more likely. Specifically, we want the probability of observing a 100 to be 3 times larger than the probability of observing a 1, and we want those probabilities to ramp up linearly. So if I were to draw, say, a bar chart that gives the shape of this distribution, well, here's what we see. We see a nice linear increase in probabilities from 1 to 100, and indeed the height of the bar at 100 is 3 times the height of the bar at 1. So in essence, the weight we're giving to the 100 outcome is 3 times higher than the weight that we're giving to the 1 outcome here. So how do we actually convert these into actual probabilities? The heights of these bars in this case were simply just created by making a sequence that starts out at 1, ends at 3, and has a total of 100 values in there that captures the patterns that we want. But that collection of weights surely is not a probability distribution because the sum doesn't come anywhere close to equaling to 1. So how do we convert this shape into a bona fide probability distribution? How do we take that collection of weights, those relative frequencies, and come up with a set of intelligent probabilities? So our solution is going to take those weights that we like, take that shape that we like, and just to rescale those weights so that they do add to 1. How do we do this? Well, it's a remarkably simple process, so that's great. What we'll do is that if we have a vector, say called weights, where we've given each of the possible outcomes some relative frequency that we want them to have, we can make sure that we end up with a valid set of probabilities, let's call it vector p here, just by taking the vector of weights and dividing by the sum of all the values of weights. So weights over sum of weights is always going to give a vector whose elements sum to 1, and it's as easy as that. Making a bar plot now of the elements in P, we see we still have the same old shape. The probability of observing 100 is 3 times larger than the probability of observing a 1, but now the sum over all those probabilities exactly equals to 1. So another example, just to make this clear, let's imagine that we're coming up with a probability model that describes the number of purchases a customer makes over the course of a year. So 1 is by far and large the most likely value to observe, but there's kind of a peak around 8. There's a bit of variation between customers here. It goes from 1 to 15 though. So the shape is not a probability mass function because if we look at the heights of the bars, those aren't probabilities because they're not summing to 1, but we can actually fairly easily convert this into a valid PMF. How could we do this? Well, in this case, I actually have an equation that tells me the shape of the PMF, the weight that I want to give to each outcome, the relative frequency that I want each outcome to have. And in this case, it's a relatively complex equation. I've kind of tweaked the parameters so it has just the shape that I like. So how would I turn this shape, this collection of relative frequencies, into a bona fide PMF? Well, I just need to rescale the values of the shape, those weights, so that the sum of the probabilities do add to 1. And here's my process, and this is going to work every single time. Step 1 is to create a vector x that lists out all the possible outcomes you might observe. In this case, the integers 1 up through 15. Then define a vector called shape that gives the weights that you want to assign each of those outcomes. The first element in shape should be the weight you're giving to the first element of x, so on and so forth. So you can check to see if you lucked out and you have a valid PMF just by taking the sum of the shape values, but it's really never going to equal to 1. But easy enough to convert that into a set of probabilities. All you have to do is take your shape vector or your weights vector, divide by the sum of those values, left arrow that into P, and every single time you're now going to have a set of probabilities that form a valid PMF. All right, so doing that process, we see that P, left arrow, shape over sum of shape, does indeed equal to 1 when we take the sum of the elements of P. So contained in P now, we have a nice valid PMF. And we can actually convert the equation that we're dealing with into an equation for a valid PMF by doing something very similar. So in this case, we started out with an equation that gave the heights of those bars, the shape that we really like, the relative frequencies, those weights. And if we want to convert that into an equation that actually spits out probabilities, we just need to make sure that those probabilities sum to 1. And here's the procedure that's going to work every single time. Kind of along the same line that we did before, what we'll do is define that vector x to contain all the possible outcomes we might observe, define a vector for shape or weight that gives those shape equation, and then look to see what the current value of shape is, sum of shape. So in this case, we get 3.135, etc. All we have to do is take our equation for the shape, put a big old pair of parentheses around it, and then multiply that by the reciprocal of the current sum of the values we have in shape. So this equation right here, 1 over 3.135, etc., times our original equation for the shape is going to be an equation that gives a valid PMF here. So pretty easy way to convert from just a shape to a valid probability mass function. There's a procedure that's going to work every time. If you just want to have a vector in R that has all of those probabilities P, or if you actually want to come up with an actual equation that tells you, if you were to just plug in various values of x, what the probability of observing that value of x is going to be. Actually, as a bit of a side note, we've used sample in writing Monte Carlo simulations really quite a bit. Behind the scenes, that's exactly what sample was doing. When we passed it that prob equals argument and gave it a vector of weights to assign with each of those outcomes, we didn't have to worry about making sure it was a valid probability distribution that all those summed to 1. We just gave it a list of numbers that told us the relative frequencies of each of those values. Behind the scene, that's exactly what sample was doing. It was taking that vector of weights that you had given to it and just said, okay, I'm just going to rescale them by taking the values I see now, divided by the sum of all the values, and that's going to create a valid probability distribution. So sample knows where it's at, that's what it's doing, and so we can do the exact same thing to convert a shape into a probability mass function. So one more example, let's imagine that we had an equation whose shape that we really, really like. We want to use this to model some random quantity. X goes between 0 and 20. We have an equation for shape. How do we very quickly get out the equation for the PMF itself? All right, well, define a vector x that gives the list of possible outcomes, the integer sequence 0 through 20. Define a vector that gives us the shape, the weights to assign to each value of x. So simply just transcribe our equation for the shape in terms of x. And then sum of shape lets us know what we need to essentially take the reciprocal of and multiply by our original equation for the shape. So we wrap our equation for the shape in a big old pair of parentheses, multiply that by the reciprocal, and we're good to go. We now have an equation that gives us a valid PMF. So an equation or a table is fantastic for summarizing everything there is to know, really, about some random variable, some random process, but a picture is worth 1,000 words. Very often it's nice to visualize what the distribution of that random quantity looks like, and you can do that with the good old plot command. If you have your p vector containing the probabilities, your x vector containing the list of possible outcomes, well, plot p twiddle x will get you there. But I think making a bar chart is a bit more productive, a bit more informative in order to see what the distribution looks like. Now, bar plot has kind of a quirky syntax, so here's how it works. Once you have your PMF, your x vector giving the list of possible outcomes, your p vector giving a vector of those probabilities, well, what you want to do is run bar plot with first argument p. That first argument is going to tell you the heights of those bars, and so they'll go up to the probabilities of each of those outcomes. The second argument, you're going to say names.arg equals x. The names.arg argument just labels each of those bars, so we're going to label the bars after the value that they represent. All right, so the PMF is describing the probabilities of observing all possible outcomes to that random process. But sometimes we're interested in more specific questions like, well, what's the probability of observing a value of at most 4 or at most 10? If we're doing inventory control, those are the questions we want to know. What's the probability of observing a demand of at most 10 over the course of a week? If that's a pretty high probability, we want to make sure to have 10 or more items in stock so we don't have a stock out. If we're looking at lead times, what's the probability that the number of days it takes a part to be delivered is less than or equal to 5 days? If that's a pretty high probability, well, we could quote that lead time to a customer. So when we have questions like this, what's the probability of observing at most a particular value? Well, there's a whole function in probability theory that's devoted to answering that question, and that's known as the cumulative distribution function, or CDF. We're going to represent that with a capital F of x, and it's simply going to tell us the probability of observing a value for that random variable, capital X, that is less than or equal to little x, at most little x here. So in some sense, it's measuring the probability that's accumulated as we move on to higher and higher values of x, and this helps us answer some common questions in business analytics. So for example, let's imagine coming up with a probability model for the number of people seated at a foretop at a restaurant. So the possible values 1, 2, 3, 4, first column. Second column gives us the PMF, the probabilities for each of those values. Let's create a third column that gives us the CDF, capital F of x, the probability of observing at most that value of little x. So how would we get those values? Well, the CDF evaluated at 1 would be the probability of observing a value of 1 or fewer, at most 1 here. Well, there's only one possible outcome that's 1 or fewer, that's 1 itself. So the CDF evaluated at 1 will just be 10%, the probability of getting exactly one person at that table. What's the CDF evaluated at 3? Well, capital F of 3 is the probability of observing a value of 3 or something smaller, at most 3. So in this case, that would be the probability of 1 or a 2 or a 3. I can sum up the probabilities of those three outcomes to get 60% in this case. So that CDF is kind of measuring how that probability is accumulating. As I go up to higher and higher values of x, what's the probability of observing at most that value of x? So this has pretty widespread applications in inventory control to help, minimize the probability of stockouts. If you are coming up with a model that describes people's bids on auctions, this would be very useful. You'd like to know what's the probability that the highest bid among the competitors is at least $80 or is at most $120. If you have answers to those sorts of questions, you'd be able to strategically place maybe a winning bid. So with the cumulative distribution function, capital F, one thing I want you to keep in mind is that for discrete quantities, you need to be very careful about which symbol you're using, the less than or equal to symbol or the less than symbol. Most of the time, we'll be using the less than or equal to symbol because that goes into the definition of capital F, the probability of observing at most a value x. So less than or equal to x. There's a big difference between less than or equal to and strictly less than with discrete models because they refer to two completely different set of quantities. So less than 2 would technically be meaning the same thing as 1 or fewer. So just be really careful you're calculating the right thing. It's easy to kind of mess that up and to include a value that you didn't or exclude a value that you meant to include here. All right, so with that PDF, we have an equation that tells us the probabilities of every possible value, or maybe a table. For the CDF, we actually take it a step further and actually define what the value of that CDF is, even at values that are impossible to observe. And that's because the CDF has a well-defined value for, say, impossible values of x here, values between two potential observed values. So what do I mean by that? Well, what if I ask the question, what's the probability of observing at most 3.5 people at that foretop? Well, kind of translating that into English, at most 3.5 really means just 1, 2, or 3. And I could answer that question, that was 60%. So for CDFs, capital Fs here, I'm actually able to evaluate its value for values of x that I don't have any probability of seeing. So when we actually write down the definition of a CDF, we're going to be careful to completely encompass kind of that fact here. So for example, with that foretop, what we're going to do is we're going to be careful to include the entirety of the range of values of little x, even when there's no possible way of observing them. So for that foretop example, we can only observe 1, 2, 3, or 4 people at that table, but we're going to write capital F of x to have a definition that encompasses absolutely everything. So for any value of x that's less than 1, well, there's no possibility of observing less than one person at this table, so all values of x less than 1 are going to have a value of 0 for that CDF. Likewise, all values of 1 all the way up to, but not including 2, is going to have a probability of 10%. The probability of observing 1.9 people or fewer, 1.2 people or fewer, that's the exact same thing as the probability of just observing 1. That's our 10%. And so we're going to give it a range of values anywhere from 1, including 1, up to, but not including 2, a value of 10%. And we'll continue with that convention. What's the CDF between 3 up to, but not including 4? Well, that would be the probability of observing 1, 2, or 3, at most 3 here. That would be that 60%. And then once we get to 4, our maximum possible value, there's a 100% chance of observing that number or something smaller. And so for any value of x that's equal to the maximum possible value, or even bigger, that CDF is going to equal to 1. So the net result is that if we make a visualization for that CDF, it's going to look like a staircase. So it's going to jump whenever we run into a possible value of x that actually is observable. The height of that jump actually is going to be equal to the probability of observing that particular value of x. And then it's going to be flat all the way up to, but not including, the next possible value. And that's just reflecting the fact that the probability of observing 3.7 or fewer, it's the same thing as 3.5 or fewer, 3.3 or fewer, all the way down to 3 or fewer. And so those horizontal bars in the visualization for that CDF, they have a big round circle on the left-hand side to indicate that, hey, we do include that lower endpoint. That line at 3 that extends out to 4 includes the number 3, because it's the probability of 3 or fewer, but it doesn't include the right endpoint, the value at 4, because that's actually included on the line above that stretches from 4 all the way out to infinity in this case. So here's another example that is going to stretch a little bit of our mathematical thinking. So the 4-top example is nice because we had very few possible outcomes, so we were able to make a quick table to describe the PMF and the CDF. But what about this case? Let's imagine that we're a telemarketer and we're calling up a particular customer trying to sell them on a particular product. And if you're like me, you probably get calls for extending your auto warranty or something like that all the time. And so let's imagine that this one telemarketer is calling this one customer again and again and again and again. And let's imagine, rather unrealistically, that the probability of making a sale is independent from one trial to the next. In the real world, we get very sick of it quickly, stop answering that call. But for this example, we'll imagine the customer picks up each time and has a probability P of actually purchasing that product. So we might be interested in studying the random variable capital X, which is going to be our name for the random variable, the call number on which that first purchase occurs. So the telemarketer is going to keep calling. They're going to fail, 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 fail. Eventually, they're going to succeed. So on what call number does that sale eventually get made? Okay, well, we might like to know the cumulative distribution function for this. What's the CDF, capital F, of X? What's the probability that that first sale will occur within the first 60 calls, the first 10 calls? What's the probability that X is less than or equal to some value? Well, we need to build up to that actually by first getting the formula for the PMF here. And this one's pretty easy to derive. If we want the first successful call to happen on call little x, well, we need to have x minus 1 non-successful calls, each which happen with probability 1 minus p, the outcomes of which are all independent of one another. So the probability that the first x minus 1 calls are all unsuccessful would just be 1 minus p multiplied by itself x minus 1 times, or 1 minus p raised to the x minus 1 power. That sequence of x minus 1 unsuccessful calls followed by a success on call x. So that whole product, that 1 minus p raised to the x minus 1, multiplied by p to represent that final call being successful on call x. So not too bad, we have a formula for the PMF. Well, what about the formula for the CDF, the probability of observing a value of at most little x? Well, by definition, we can use our summation notation to say that, okay, if I have a particular value of little x in mind, I need to sum up this expression, 1 minus p raised to the I minus 1 power times p, from I equal to 1, 2, 3, 4, all the way up to little x, because I'm getting that probability of observing a little x or something smaller. And here is where you would get stuck unless you happen to learn some pretty sophisticated math tricks in other classes. So it turns out that we can actually evaluate that sum, come up with a closed form, very simple expression for this, but that's really beyond where we need to be in this business analytics class. So we're going to rely very heavily actually on Wolfram Alpha to help us out. So Wolfram Alpha is this amazing tool that allows us to do very complex mathematics with very little understanding of what it takes to actually solve that problem. And so I think long gone are the days where we really need to know the ins and outs of solving complex algebraic equations, calculus problems, etc., especially in business analytics where we want to get to the answer. As long as we have a rough understanding of what the math is doing behind the scenes, we're definitely happy enough just getting that answer directly without kind of going through the math and the learning that it takes to actually get there. So in this case, I want to figure out, okay, well, how do I evaluate that sum here. The sum from I equal to 1 up to x of the quantity 1 minus p raised to the x minus 1 power times p. Well, in Wolfram Alpha, you pretty much get to just type in English what you want to evaluate. And the natural language processor that lurks inside Wolfram Alpha does a pretty good job at figuring out what you mean. So to do a sum, I'm going to set it up like this. I'm going to take the sum, and I'm going to say, well, what do I want to be summing up? What's the component of each of these sums? I want to take the sum of 1 minus p raised to the I minus 1 power times p. I want the probability of observing at most a value of little x. So I want to take this term here and go from I equal to 1, 2, 3, 4, all the way up to x. So I want to take the sum of that from I equal to 1 to I equal to x. And it's as easy as that. Once we ask Wolfram Alpha, hey, figure out this answer, it uses its whole suite of mathematical tricks for evaluating tricky quantities, and we immediately get out that the formula for the CDF is equal to 1 minus p raised to the x power. Now, I've tweaked that expression just a little bit on this slide here. I've added the floor symbol, that kind of funny symbol that surrounds the x on the left and the right, because I know that when I'm defining that CDF, I want to come up with an equation that works for every imaginable possible value of x, even ones that I can't observe. And so since I know that the possible values of x are integers, the value of capital F evaluated, say, at 3.7 is going to be the same thing as the capital F evaluated at 3. It kind of rounds down to the nearest integer. It's going in that staircase manner here. So essentially take whatever value of x you have in mind, lop off the decimal part, take the floor of that expression, and that'll tell you the probability of observing at most that value of little x. So Wolfram Alpha, a huge lifesaver when we need to do mathematics, very useful in coming up with equations for CDFs. Sums are hard for us to do just by hand, easy for Wolfram Alpha to do. All right, so once we have our PMF, either a table or maybe an equation, how do we work with it to answer interesting questions like what's the probability of observing a little x between 5 and 15? What's the probability of getting an odd number? What's the probability of being at most 5? So how do we work with the PMF once we've got it in order to answer questions about probabilities? Well, we're going to exploit that fact that our possible values of x are all mutually exclusive. So when we have a question like what's the probability of observing x2 or x5 or x6, we just get to straight up add the component probabilities of each of those events. So how are we going to do this in practice? Well, in R, unless we want to do it by hand, and you can do it by hand if you want, in R, here is what I'm going to suggest. And this will work every time for you. So if you want to use a PMF to answer questions about probabilities, first define your vector x to be the vector of possible outcomes you might observe. And then define your vector p that gives you the probabilities of each of those outcomes. So the first element of p should be the probability of observing the first element of x. The 10th element of p should be the probability of observing that 10th element of x. And then what we're going to do is we're going to construct an expression that looks like the following. Sum, then in parentheses, p bracket, and then some sort of which function that references the x vector and a logical condition. Let's break this down so we can be clear about how this is going to work. This is a good time to review the which function and some of these other logical conditions that we need. So let's imagine that here is my PMF. I'm going to take the sum of my values inside the p vector to confirm that I didn't typo. They do sum to 1. I'm going to make a bar plot to visualize what this probability distribution looks like. So here I have some random quantity under consideration. The possible values are 0 up through 7, and those are the respective probabilities. So what if I wanted to answer the question, all right, well, what's the probability of observing a value of exactly 3? Well, I could print out that vector of p to the screen here, and as long as I'm careful about what value each of these elements reference, I could just do that visually. I know that the first element of p corresponds to the first element of x, so that's 0. So if I want to know the probability that x is equal to 3, that would be the fourth element of p. And now you can kind of see why we might want to actually do this more efficiently, because depending on what the possible values of x is, you might have to reference kind of peculiar looking elements of p. It's kind of weird the probability that x is equal to 3 is the fourth element of p. There's got to be a better way for this. So here is going to be my suggestion. Once we have our vectors x and p that are lurking in that global environment, we got our x, we got our p, here's what we want to do. We're going to use the sum, the which, and some logical condition to figure this out. So here's how we're going to construct it, and here's how I'm going to recommend you actually construct these statements. So you're going to ask yourself, okay, what's the question of the x's that's being asked? So in this case, what's the probability that x is equal to 3? And you're going to write out the logical condition that describes what you want to be discalculating here. So x is equal to 3 here. And then what you're going to do is you're going to say, okay, well, which elements of x are equal to 3? You're going to wrap that logical condition inside of the which function. Now remember, what which does, it dives inside of a vector and it lets you know where, position-wise, inside that vector, you find elements that satisfy that logical condition. So in this case, there's only one element of x that is exactly equal to 3. It's letting us know that, hey, that's that fourth element of x here. All right, well, I know that the p and the x vectors are defined so that they match up with each other element-wise. The value in the fourth element of p is the probability of whatever the fourth element of x happens to be. So if I say p bracket, extract out the element of p in that position, inside the fourth position in this case, I get a 0.15. And just for good measure, because I might have been asking what's the probability of more than one outcome, I can take the sum of this in order to always get the answer. So that's going to be my recommendation. If you have a question, a probability question about the outcomes, first write out the logical condition that describes your question, then use the which function to figure out which elements of x correspond to those outcomes, put square brackets, that which function inside the square brackets, and extract out those elements of p, and then take the sum of those. So, for instance, what's the probability of getting a value of at most 2? Well, at most 2 would be x less than or equal to 2. So where do I find values of x that are less than or equal to 2? Well, just running that as a command, I get a bunch of trues and falses out. If I put that inside of the which function, though, it lets me know that the first, the second, and the third elements of x are less than or equal to 2. Confirmed. So let's extract out those values of p in those positions. We get these three probabilities, and so we can take the sum of those three probabilities to get the probability of observing a value of little x that are less than or equal to 2. So no matter what the question, that's what we're gonna end up doing. So we'll use our logical condition in order to figure out which elements of x correspond to the outcomes that we want to be calculating the probabilities of. And then we'll put that which command inside square brackets referencing p in order to get out the probabilities corresponding to those outcomes, and then take the sum to get our final answer. So, for example, if I wanted to know, well, what's the probability that x is between 3 and 6, doesn't include 3, but it does include 6 here. Well, the way that I would write that logical condition would actually be to combine two logical conditions separated by the ampersand. Unfortunately, R doesn't know this logical condition just writing like a range of values. You actually have to write two conditions that give you that range. So x greater than 3 and x less than or equal to 6 describes that logical condition. We'll put that inside of a which, put that inside square brackets referencing p, put that inside of a sum function, and there we go, we have our values. Now what if, though, the possible values of x we might observe are infinite? We can't create infinite size vectors in R, so what's going to be our trick? Back to the telemarketer example, we're trying to study the call number on which that first successful sale occurs. Each call has a probability of 10% of success. Our PMF has the following equation. So infinite number of possible outcomes, x can be 1, 2, 3, 4, up to infinity. And so how do we go about actually doing this? So my favorite trick is to realize that, hey, for some values of x, these probabilities are going to be so tiny that for all intents and purposes, we can ignore them. So what I'm going to do is I'm going to define as my vector x just a range of possible values of x that contain almost all of the probability. So in this case, I'm going to define x to be call number 1 up through call number 1000. I'll define p to just be my equation for the PMF transcribed. And I'll look to see, okay, did I include enough values of x to encompass almost all the probability? Notice that sum of p in this case does evaluate to be basically 1 to machine precision. And if I look to see, well, what's left over, what's the difference between 1 and the sum of p, I get a value that's like 10 to the minus 16 power. So definitely close enough. So if you do run into a case where you have an infinite number of possible outcomes, just include enough so that you've encompassed most of that probability. And then it's going to work the exact same way. I want to know what's the probability of x being, say, greater than or equal to 4. Well, I write out my logical condition, x greater than or equal to 4, wrapped inside of a which function, wrap that inside of square brackets, referencing p, and then take the sum of those values. So we're automatically having R extracting the values of p that correspond to events that we're interested in, values of 4 or bigger, and we're summing those up all in one line. So one last thing before we move on to our tour of the zoo of notorious distributions, distributions that arise quite often in business analytics, I did want to relate this back to basically Unit 1, where we talked about what probability was defined to be in terms of sample spaces. So way back then, we said that the probability of an event was just the fraction of the sample space that contains that event. So if I wanted to know what's the probability of rolling a 7 if I roll 2 die, all I have to do is write out that sample space, all the possible combinations of values I might see on those 2 dice, and then look to see, well, what fraction of those values correspond to my event of interest. 6 out of those 36, the probability would be 1 out of 6. Let's do something similar here, but represent our sample space as the area of the bars that present that visualization of the PMF itself. So for example, let's imagine I'm dealing with the following PMF. Here's my bar chart. Now, one nice thing about these bars is that the area of each of the bars exactly equal the probability of observing that outcome. So the widths of those bars are always equal to 1. The height of the bar goes up to the probability of that event. So the area, width times height, is going to be the probability of that event. And since we know the sum over all the probabilities, over all possible outcomes equals to 1, one thing that we know is that the total area that's kind of fenced off by that bar chart is going to equal to 1 itself. So there's a nice analog. If I ask, okay, what's the probability of observing a value between 2 and 4, 2, 3, or 4? Well, that's the fraction of the sample space where I find 2, 3, or 4. That's the fraction of the area of the bar chart that corresponds to values of 2, 3, or 4. The total area of the bar chart is 1. The total area of the bars devoted to 2, 3, or 4 would be what fraction of 1, or basically what percent of that sample space corresponds to my event of interest. And this will tie in nicely when we start talking about, well, how do we calculate or think about the probabilities of continuous quantities.